So, final presentation session of the conference. So Phil is going to chair it very kindly, but yeah, structures, drainage, and infrastructure, and we've actually got 4 presentations because there were that many good submissions. We included 4. So I'll let Phil take over.
Yes. So structures, drainage, and infrastructure. Last but not least. And our first presenter is Thomas McDonald from the University of Newcastle.
Thank you. Okay, I'll quickly check. Can you all hear my voice all right? Brilliant. So, hello everybody. Pleasure to be here today. Thank you for having me. So my name is Thomas McDonald. I am a 4th year PhD research student in the Centre of Excellence for Mobility and Transport at Newcastle University. My specialist subject is the 3D visualization of a new form of ground penetrating radar for the rail industry, which is called hybrid rotational GPR. Spoilers, that's what it looks like on the right hand side. Meant to say, by the way, my background, Sam, you stole my thunder here. We seem to have had the same upbringing, as I was also an applied mathematician by training, only I specialized in quantum vortex dynamics, and then someone said, we've got some complex radar data to visualize. Would you be interested? And I, of course, leapt at the opportunity. Is that going to work? Aha. So I should probably start by motivating why do we care about subsurface inspection of rail infrastructure. Usually when we talk about radar and the railways, we talk about measuring the track bed, looking for ballast fouling and other sorts of issues underneath the rail tracks. Not much thought is really given to defects that occur within structural walls, retaining walls, and the crowns of tunnels. And if left undetected, particularly in our aging infrastructure in the UK network, small nucleating defects like those you see in Figure 2 can rapidly grow if not picked up on. And this can weaken and debond the masonry, which in the case of this tunnel in Luxembourg can prove quite problematic to oncoming traffic. We want to avoid this, which means, as I believe Mark said earlier, interception early on is much better than trying to react to it after damage is caused. Many attempts have been made to use radar in railway tunnels and non-retaining wall structures. I call this fixed directional ground penetrating radar, in that antennas point in rigid directions, like the rig you see on the right-hand side. The problem is with these rigs that you always typically end up with some form of limitation to your survey coverage. In that case, you can't really inspect the lower side walls or the track bed. And a key problem is the clarity of the output data. Now, I'd say hands up what you can see here, but I wouldn't expect anyone to be able to read off the bat what they're looking at here. This is an example of a conventional 2D radargram from a GPR dataset. On the right-hand side, we make these datasets up by lots of individual trace measurements. You move to a location, you take a scan, and what the radar does is it transmits a radio signal into the ground, which partially reflects every time it comes across a material discontinuity or medium change. The bigger the contrast between the electrical properties of 2 materials, the stronger the signal, the more black, in this case, the image becomes. And what happens is, as the radar's moving, it's a conic beam. It can see a little bit ahead of itself and a little bit behind itself. So as you're moving over a structure, you'll start seeing a hyperbolic pattern appearing. Even with several years of training, most radar engineers have to consult external bodies in order to understand what they're actually looking at in these images. To give you an idea of what this image actually conveys, we're looking at 3 separate pipes and the material boundary on the left-hand side. But if I was just to show you that on its own, it's not immediately clear what you're looking at. Therefore, it's desirable to make this information more accessible to infrastructure managers and other members of the transport group, that we want more intuitive 3D style output. We want to see what we're looking at in its true spatial form. A way of achieving this is to use more comprehensive data sets. In other words, make a full scan of a full 360-degree profile of your railway tunnel. However, there wasn't, when I started my PhD, a dedicated tool for doing this. And working with Railview Limited and Euromobilita, the rig on the right-hand side called Tunnel Vision was developed. This is a unique system in that it has a 360-degree orientable antenna, which massively increases the coverage of the subsurface of the structure. And by subsurface, I of course mean anything which is behind the structure you can put your hand on. It's not always below your feet. Uniquely, the system has independent control of rotation, both laterally and azimuthally, meaning it can get planar data sets where you fix the rotation as you move forwards, creating a raster scan. You can perform individual rotational transects, move forward and then scan. And uniquely, you can perform helical transects wherein you continuously rotate as you move. That's a bit beyond the scope of the work that I've been looking at currently, but that is the next step of innovation to study those new exciting data sets. In order to improve the rig you see on the right-hand side, it was necessary to increase the accuracy of the antenna bore site. How do we know exactly where it's pointing? Therefore, where can we position these defects? Most important that we can return to a surveyor, you have a problem approximately 100 meters into the tunnel on the left-hand side near the top of the tunnel structure. And we also want more intuitive output. How do we get that output to be 3D rather than 2D hyperbole? So there was an opportunity here to develop these 3D visualizations. I needed to build the necessary algorithms and hardware innovations to make this a reality. It needs to be efficient, it needs to be versatile, and most of all, the mathematics need to be tractable. On the right-hand side, this is the full algorithm that I came up with. I don't want you to focus on the individual components per se. I want you to look at the three main headings, which is we had an extraction and pre-processing phase, followed by a grid regularization phase, followed by a cluster segmentation and rendering phase. And the brilliant thing about this architecture is that it's entirely modular, meaning that we can pull out and put in different modules in order to modify and update the process as time goes on. This was accompanied by several hardware updates, namely the increase of the positioning accuracy, which was achieved using stepper motor control, and also miniaturization, as that massive rig was great for deploying in a real tunnel, but not so good for laboratory tests. The 3D profiling procedure also had to accommodate for the leading simulation software. If you want to have exact knowledge of ground truth geometry in your system, you're probably going to want to simulate first. And leading simulation tools, whilst they can handle 3D environments, they still give you 2D output data. Therefore, this procedure had to account for helical data sets, had to account for planar data sets, and those gathered with a rotating antenna. 3 different types of interesting inputs, all of course in different file formats because naturally. I want to take the work slightly further towards the end of my PhD, namely, we have 3D output, how can we make the spatial resolution better? And I'm going to share with you the work I've been doing on that now. So the first of the experimentations that I performed was to have a look at 3D simulation. It is most natural that you want to analyze how well the 3D workflow performs when you have absolute knowledge of the geometry and defects that you are looking at. The way this works is I use a software called GPR Max. It's an open source simulation package, and I perform area scans of this unit, which equates to dragging a virtual antenna across the top of this material medium, which contains 3 control spheres as targets. And the idea is, how do I get those spheres back using my reconstruction method? The main challenge that came into all of this was how do you perform area scan simulations in this software when it's not natively supported, for which I came up with a solution which was based on batch processing via shell script automation. Moving on from the simulation work, I will show the results on later slides, by the way. I want to show you all the experiments first, followed by what we found problem. Once the simulation validated the performance of the 3D mathematics, the next step was to apply it in a more realistic environment of physical data, but in a noise-controlled environment to get an idea of exactly how the geometry is interacting with the procedure. To do this, the same geometry setup was created in reality in an anechoic chamber environment, for which I first passed a commercial Zone 12E radar system over the inspection area. This provided me with, again, a comparable measurement based on realistic data. Notably, I had to add outriggers to the operators because, as I mentioned prior, the radar sees ahead of itself as well as behind. Therefore, it is insufficient to simply move a radar over the area of interest. You need to move it slightly further and slightly behind in order to capture everything properly. Following on from this, that fixed directional data provided a baseline comparative reference for the new experimental miniaturized hybrid rotational radar system, which I developed from scratch during the project. This system worked on the principle of rotational transects. Namely, we move over the same sample with a downward-facing antenna moving approximately 50 degrees of sweep, taking step frequency GPR measurements throughout its pass. Namely, we move to a position, perform a rotation scan, continue to move forwards, and repeat. That built up a dense 3D point cloud of over 2 million individual data points, corresponding to almost 4,000 individual trace measurements. Following on from the laboratory work, upon validation, the work progressed on towards practical validation in a full-scale tunnel subsurface analog. Now, it's not very easy to go up to a tunnel operator and say, I would like to put a defect behind your wall. They look at you very funny if you try and do that. Therefore, I needed a solution which allowed me full control over the subsurface geometry whilst providing a large enough reference area for a practically sized data set. The solution was to head to Chesterfield, and I worked with the University of Derby on designing this rig. And the solution was to use submerged pipes in a utility bed, backfilled with ballast, and this inspection pit formed effectively a partition section of my pseudo-tunnel wall. And basically it's below us, but the point stands this could be translated realistically anywhere around and provide a comparable handling. Target geometry in question was 3 hollow plastic pipes, the next complexity layer above spherical metallic targets. Namely, if I could reconstruct exactly where they were, this would give strong indication that the procedure was working in accordance with expectation. And to achieve this practically, the measurement data was collected using a vector network analyzer with automations controlled by a Raspberry Pi 3. And in this situation, the position was controlled manually by human operation. From this sped up footage I'll show you now, albeit a bit jittery. Over the course of a day, I progressively scanned over the entire region of test material. And the reason I'm doing this by manual advance rather than motors was down to the fact that at movements over a meter, you had time to accelerate and decelerate your apparatus. In movements of less than 1 meter, it was much easier to decelerate this apparatus simply by using the handbrake. Following on from the work that was done in the inspection pit, the next step, as I mentioned prior, was coming up with a refinement of the visualization clarity. How do you make the spatial resolution more accurate? To do this, I looked at several options, but the most natural way of doing this was to perform yet another experimentation. For this one, I shifted focus from specific tunnel walls to more general retaining walls, this time on a masonry-based structure. And the idea was we have metallic targets behind the wall, which we wanted to image, but the idea was that with a conventional approach, you would see the metallic targets at the back and the front and rear interfaces of the brick wall. The idea was, after running the spatial resolution enhancement method, which was a combination of inverse fast Fourier transform and multiple signal classification, collectively known as CPM, combined processing methodology, that after this it would be possible to view individual layers of brickwork within your signal traces. Right, I'll have a whistle stop now because I'm conscious of time through the individual results. Collectively, this is the work that was recovered from the laboratory experimentation. That includes the simulation work in Figure B, the fixed directional movements with the outriggers in Figure C, and the hybrid rotational laboratory apparatus in Figure D. And what's reassuring to see here is that the larger 100mm sphere targets and the smaller 60mm sphere targets consistently manifest within the output data sets. Admittedly, there is a slight rotation involved between the geometry configurations in the former and the latter, hence the notation of the data set. But the good news was that in recovery of these methods, that the decimeter length scale targets repeatedly and consistently appeared within the output data, which provided a more than sufficient bounding box domain to inform a structural surveyor that there is a defect present within the structure. Notably, the mid-centers of each of these targets agreed with the ground truth geometry within an impressive 3.4%, which is significant, which is more than ample in order for a defect to be localized and identified within a working structural body. And in the process, I optimized the cluster sizes that we used for the segmentation procedure, and it was found that clusters of about 150 data points or more gave the most consistent with reality results in this case, which is a fantastic step forward. In the progression to the field tests and the other structures, the 3 retaining pipes, each of them in turn were discovered, and the runtimes for these visualization generations were the order of about 60 minutes for the 2.5 meter by 2.5 meters by meter deep data sets, which on upscaling through assuming a 0.5 kilometer tunnel would provide a reconstruction work within the order of days to weeks versus what we currently have, which is very limited data to do that job with anyway. So that would be a fantastic step up on what was currently achievable with existing radar technology. I will note that you will see there is an additional target in Figure A, even though there's only 3 pipes. This is a result of ring down phenomena. When you have a hollow target, your radar signal can resonate inside it, which means that the reconstruction method has the potential to fragment one body into two. Looking into the future, this is a challenge I'd like to overcome with additional work and looking into perhaps AI-based reconstruction methods. Okay. And on the topic of signal spatial resolution enhancement, the overall result was a 152% increase in the resolution of the individual spatial profiles based on the baseline provided by the raw inverse fast Fourier transform result data. And in mentioning those bricks that we mentioned before, what we can see between 9 nanoseconds and 11 nanoseconds in these individual traces is the formation of smaller, sharper peaks. That is the detection of your brick interface boundaries. The next natural progression for this work would be to move into high dimensional settling in 2D and 3D. Currently the work is only explored in one-dimensional space, simply due to the time availability and the amount that we have going on at the time. Looking to the future, I see 3 key areas that this technology could develop and 3 key areas I'm very interested to pursue. Formally, technology and knowledge transfer, looking at embankments, drainage systems that have been mentioned in previous talks. This technology has the ability or has the potential to be part of autonomous multi-sensor inspection vehicles going forward. And a natural pairing of this would be photogrammetry and LiDAR systems, such as those you see on the left-hand side, which collectively can form comprehensive 3D data sets, which have the potential to form virtual survey environments with the addition of extended reality hardware. This would be a game changer for the rail network in terms of getting boots off ballast, as it would mean you wouldn't have to go directly onto a site in order to take some inspections, not only of the surface structure, but also defects behind your structural inspection surface. And lastly, building a development platform for future generations of radar-based researchers and infrastructure enthusiasts based on open source programming in the field. Tools that could do this, not only my visualization methodology, but also GPR Max, as I mentioned before, and also the GPR PUI program for 2D data processing and commercial tools. So yeah, I'd like to thank you all very much for your time and listening to my research practice. We had a look at the methods that we used, what 3D visualization of HR GPR is, and some exciting potential further development opportunities going forward to the future. Thank you very much to the sponsor of the project and the industry partners, and I'd like to thank you all very much for your time. Thank you.
Thank you, Thomas. We have time for 1 or 2 questions, if there's any in the room.
You mentioned putting it on potentially monitoring vehicle. How fast do they have to travel in the time of the business?
It's currently subjective to what type of radar you are actually employing. Although I glossed over, there are 2 methods of radar which I trialed during my research. The early one you saw, which was the T-Vision system, that was based on step frequency GPR. Therefore, movement speed for this sort of configuration, partly to ensure you don't introduce any additional vibrations that could upset the apparatus. That was of the order of 1 to 2 kilometers per hour for those systems. Whereas the impulse systems, which you saw from the fixed directional unit, which is the more conventional for ballast inspection, you can achieve speeds upwards of 60 kilometers per hour, so 60 miles per hour, upwards of 100, subject to your choice of measurement. Fingers crossed. Does anyone have any further questions?
I think that's about all we've got time for. So thank you very much, Thomas.
No, thank you for your time.
So next we have Mukatit Atalan from Heriot-Watt University, who's talking about debonding behaviour in slab track railways.
Good afternoon, everyone. Thank you very much for giving the opportunity to present my research. My name is Mukatit Atalan, and today I will briefly discuss our research on the debonding behavior on slab track systems with helping the 3D dimensional finite element modeling. And this research was conducted from the University of Nottingham using the HPC facilities, high performance computing facilities. As many of you know, the slab track stems are widely well known, their stability and the um, low maintenance requirement, which is why they preferred widely nowadays. However, the one major challenge that threatens their reliability is debonding, which occurs the wedge layer within the slab, losing the adhesion. The loss of the adhesion can have a serious consequences, leading to the increased noise and in the worst case scenarios, maybe it might be the structural failure. Therefore, investigating the debonding issues is significant to ensure the long-term performance of the slab track stems and the safety of these systems. So let's have a look at some challenges in more detail. As we know, the slab track stems can suffer from some problems such as cracking, the formation of the air voids, the bond failure, even the foundation failure. On the top of that, environmental factors like the freeze-thaw cycles, rain and roller and the solar radiation make the worst of these problems, making it even more difficult to maintain the structural integrity of the tracks. With these challenges in mind, in this study, we aim to answer as a key questions: how does the debonding affect the structural integrity and the performance of the various slab track designs? To deal with this, we developed a 3D finite element modeling, and that's enabling us to analyze and compare the performance of the fully bonded versus debonded scenarios. In terms of the methodology, we used the Abacus software to develop a 3D finite element model, focusing on some key factors such as the contact behavior between the wheel and the rail, and interaction between the layers as well, and the dynamic conditions, of course, like the moving loads. We also give attention to the boundary conditions, time step meshing measuring and ensure that the model reflected the real world scenarios. When we move on to the validation and the comparison to our results, we set up the model using the Let's Cut data from this site in Sweden. It's quite popular. When you look at the Let's Cut cases, we have many papers related to this Sweden sites. That site has allowed us to simulate the realistic conditions. We validated our models with the study Y as a slab track systems on the left hand side, and then we compared our result with the ballasted tracks, and then we get the really good agreement with the slab tracks. But when we come to the ballasted tracks, we'll have seen some uplift when we come to the critical speed of the ballasted track. The decision only using the 5 bogies, we haven't run the full trains because it's going to be time consuming. We're just focusing on the front bogies because the maximum deflections and the maximum dynamic effect is occur on the front, actually it's on the locomotive side. So for this reason, we just run the 5 bogies on our simulations. As a summary of methodology, we employed a 3D element analysis, and then we validate our model. Then, following the steps, we prepare the model to simulate these scenarios under the both full bonding and the debonding conditions. Now, because we focus on the 3 types of the slab track designs, the first design on the left side on the corner, we name actually asphalt base track slab just resting on the 30 centimeters asphalt base supporting layer over an embankment of 1.5 meters long, and followed by the several layers of ground. And the second one on the right hand side, we named the cement base track CBT. That's the slab over the 30 centimeter cement base supporting the layer again the ground. The last one is at the bottom is the hybrid track. We named the hybrid track. We combine the features of the both asphalt base track and the cement base track with the 22 centimeters asphalt layer just underneath the supporting layer cement base. When we look at the debonding occurs in these designs, we simulated the fully debonded surfaces by setting the cohesive strength at the zero at the interface between the slab and the underlying layer. This approach simulates a complete loss of the bond, which is the critical assessing to the when the debonding happens under the extreme conditions. For comparison, we also simulate the fully bonded scenarios using the tie constraint in abacus, which prevent any relative motions between the layers, effectively representing the perfect bonding. Our results show that the bonding when you see that on the left-hand side, you will see that some oscillations happen at the beginning of the simulation. That's the debonding models, because when the debonding happens, the analysis will start to adjust itself and recalculating the modeling. So this oscillation is coming from the debonding. When the debonding happens, we see that some significant increases as seen in the figure A in ABT tracks, and also we compare the three track designs on the right hand side with the 57 meters per second. Sorry, I can't see. I'm gonna look like that. Okay, no, I was wrong. So similarly, when we come to the I guess that's not working. Sorry about that for us.
Is this one you want? There's two of your presentations.
Sorry again, that's right. So let's try the displacement. Again, it's not working.
You might have to just
Okay, just
still not there.
yeah. Okay, now I will click on manually, no problem. Similarly, when it comes to the vertical stress on the top of the embankment surface, debonding also leads to the significant stress on stress increases. For debonding scenarios, the ABT track, we call asphalt-based track, reached approximately 37 kilopascal, while the fully bonded scenarios, but it reached around 32 kilopascals when the fully bonded scenarios. This represents a reduction of around 15% when we have the fully bonded scenarios. When comparing the designs approaches shown in figure B, the hybrid track designs under the debonding scenarios that continues perform well, showing the peak vertical stresses around 22 kilopascals. So now focusing on the tensile stress at the slab bottom. Under the debonding conditions, the asphalt-based track, again, the peak tensile stress levels rise to the approximately 1.2 megapascals. And in contrast, under the full bonding conditions, the asphalt-based track maintains a peak tensile stress, and that comes around 1 megapascals at the bottom of the slabs. Among these three designs, again, hybrid track designs stands out as its resilience and the better solution for the debonding scenarios. To complete our research, and we just realized the debonding significantly impacts on the track performance and leading to increased displacement and stress concentrations, particularly in the ABT and the CBT designs. This highlights the importance of the strong bonding behavior between the layers to ensure the long performance, structural integrity, and the performance. Among these three designs tested, the hybrid tracks emerged as the most resilient options, effectively combining the strengths of both asphalt and the cement materials to provide a more stable track bed underneath both bonding and the debonding scenarios. In summary, I would say the material selection and the debonding integrity is the significant for the long-term life for the trucks and the reliability of the slab track systems. Thank you very much for listening. Is there any questions for that?
Thank you. Is there any questions?
Yeah, questions on that.
Thank you for presentation. Well, when modeling the supporting layer, such as asphalt and cement, we will consider
Pardon?
temptation.
I can hear you quickly. Sorry about that.
Shall we state the microphone?
Yeah, first, it's on the corner.
I mean, we modeling the supporting layers.
Yeah.
For the asphalt and cement. Did you ever consider temperature?
Temperature, no.
Because for the material, the quality, especially for the cement, we have some they are very good at temperature. So basically, since we model, we need to consider also temperature because it will influence the strength of the layers.
That's just right. This research is just focused on the debonding effect on the left track systems. We consider the nonlinear behavior as well on asphalt, but we needed to limit our research to keep it during the future time.
Thank you.
Is there any other questions? I actually have a sort of two-part. Me? Oh, sorry. Well, I don't know how the mic works, so it's gone. So it's a two-part question, almost. So when you describe the hybrid track sort of layer, it's cement over asphalt.
Slab, cement supporting layer, and then asphalt. We put asphalt layer.
Is there a reason for putting cement on top and asphalt underneath?
We have that model as well. We called CBT, slab, supporting layer with the cement based, and underneath the embankment.
And how does that sort of, was that in, that wasn't in there, was it?
Yeah, that was in CBT, yeah.
So why do the cement and asphalt ones behave differently? What is it in the materials that make them?
The reason they behave differently because the asphalt, is nowadays really popular to putting the trucks because of the reason to the absorbing the energies, reducing the vibration as well, and also asphalt is have the non-linear effect as well. For this, it's behaving the different between the cements, concrete and the elastic materials. That's gonna say. So for this, it's behaving different here.
Thank you. Is there an environmental benefit to one over the other? We've talked about decarbonisation a lot over the past few days. Is asphalt better than cement? I know cement's got quite a large carbon.
If we modernize our systems, might be the solution for the asphalt because it's easy to apply the fastly when we compare with the cement material because we need to frame for that, but that's going to reduce the time to build the trucks as well. So maybe that one will help the environmental effects as well.
Thank you very much. Any more questions? Thank you very much.
Thank you very much. Thank you.
So our next presentation is from Chris Taylor from the University of Nottingham, discussing the defect level approach for life cycle modelling of railway bridge components. the clicker working before we start?
Yeah.
Okay, good. Thank you.
Hi, so my name's Chris. I'm working in the Resilience Engineering Research Group at the University of Nottingham, and this work's been sponsored by the Structures team in Technical Authority and Network Rail. So Network Rail own most of the railway infrastructure, as we've heard, including 26,000 bridges, many of which were built in the 19th century. Bridges represent a critical vulnerability to railway safety, and as such, Network Rail use forecasting models to support their intervention regimes, particularly when it comes to requesting budgets from the Office of Road and Rail. We live in a cost-constrained environment, and they have to justify their spending in order to deliver a safe functional railway, and forecasting models form part of this responsibility. So lifecycle models or forecasting models comprise of two key components in the context of infrastructure assets. There's deterioration, which is sort of the left alone natural condition over time, and then intervention, which is the condition, the effect on condition from repair activity and maintenance work that's designed to lengthen the lifespan of an asset. Network Rail, in their bridge forecasting models, use a Markov model, it's like a state-based model, and they typically do them at the component level. They're also called minor elements, which are like particular components of a bridge. And they do this by the condition of each element or each component is given by the condition of the worst defect that's present on it. This is very useful for modeling deterioration, but for modeling intervention, it gets a little bit trickier because when you simulate that an intervention is performed, you improve that worst defect without knowledge of the other defects that are on that bridge or on that element. You don't know the condition after intervention. So that's where the defect level approach comes in, where we're simulating the creation and growth of defects on each component of a bridge. And this is really motivated by that intervention modeling, where we can say, where we can choose according to certain criteria which defects to improve on the element, and then the condition of the element then depends on the defects that we choose to leave behind. And this is more representative of Network Rail's bridge maintenance policies. So to do this, rather than using a mechanical model, which is what most of the models that have been talked about today have been, I'm using a state-based model, using a PetroNet, which is a graphical modeling tool, where you have sort of this network of nodes made of places and transitions and directed arcs between them. Places typically represent possible system states. So in my context, it would be the status of a defect. And you have tokens, which represent objects that move throughout the network, representing changes of state. We have transitions between them, which manage the flow of these tokens. And these typically work by, they become enabled when there is a sufficient number of tokens in the input places, and they fire moving tokens to the output place. This modeling is enhanced by introducing timed transitions, where upon becoming enabled, the transition waits a certain amount of simulation time before firing, and then enhanced further by introducing stochastic time transitions. So upon becoming enabled, it draws a random holding time before firing from a particular distribution that we've given it. Colored PetroNets refers to the token's color, which means that they carry around kernels of information so that the transitions can interact with different tokens in different ways, meaning we can build quite complex models with quite simple network structures. So this is the basis of my deterioration model. I have three different subnets here that are sort of independent from each other, and well, they're not independent, but you can model them independently. And these represent the three main deterioration mechanisms which affect metallic bridge elements. The places represent deterioration states, and this is based on the Network Rail severity extent scoring system. So it's a two-dimensional scoring system where severity in the context of corrosion is like the depth of corrosion, and extent is the percentage of the surface area of that element that's being occupied by that defect. In between each of the places, we have an exponentially distributed transition. So this is to match up with the Markovian modeling that Network Rail already do. And so it means that upon a token, a defect being put in a particular place, then the transitions will draw a distribution which represents the amount of time that we expect that token, that defect, to remain in that state. In the context of the wider model, this is a simplified version of one model that includes all of the sort of Network Rail practices. So we have deterioration along the top, and then an inspection module. So this is a complex interaction of transitions, which represents Network Rail's inspection practices, where they record the worst two defects that are present on any element. And then that goes to the reporting module, where we have, upon inspection, we update the condition of the minor element of the bridge, of the portfolio, as well as scheduling the next inspection according to network rails practices, which is a risk-based scale. So bridges that are in a worse condition receive inspections more often. So we talk about calibrating this model. What we're talking about is calibrating those exponential distribution parameters. And rather than doing this on an individual component, we decided to group assets together, group components together, according to types, so that's their function on the bridge, and then the structure type on the bridge they sit on. So an overlying bridge carries traffic over the railway, and an underlying bridge carries the railway over some traffic, over some obstacle, like a watercourse or a road. And then we've used the data from Network Rail's detailed examinations, which is their inspections, with the worst 2 defects on each monorail. We've arranged these into exam pairs, so rather than looking at the whole history, we only care about 2 consecutive exams with an interval between them, because we're using the memorylessness property, which is something that, again, it comes from the Markovian modeling. And after filtering for instances of intervention, if filtering for improvement, which indicates an instance of an intervention, we have the results that are due to deterioration alone, and we have around 5,000 to 26,000 exam pairs for each asset group. And the data that I've got is from around the year 2000 to 2019. I'll receive an updated package of data to update the model shortly. So really the optimization problem is finding a set of parameters for each asset group that describes how we expect it to deteriorate through the corrosion states. And it's a maximum likelihood estimation approach where we try and maximize the set of parameters, the log likelihood for the set of parameters over all of the observations. The trick then is to find that likelihood equation. For Markovian modeling, it's quite simple. We have the exponential Q matrix. But for my model, the trick is the difficult part comes from the data that we have is at the element level, but I'm modeling at the defect level, and there's not a one-to-one mapping between the two. So what you kind of have to do is go through all of the possible defect states that represent the start state, and then the same for the end state, and then find the joint probability distribution of those multiple defects occurring. And this is this analytical equation here, which allows for efficient computation of the cost, so we can model quite effectively. And it also allows us to use Google's JAX package for automatic differentiation, which allows us to find the derivative of the cost function without having to rely on numerical methods. However, it has meant that we're limited to only modeling 2 defects, the worst 2 defects on a particular component, due to extent constraints. So where we have like you can only try 100% of the component, and then you'd have to start considering absorption and cannibalization of different defects, and that means you have to rely on sampling, which would slow down the whole situation. So we've gone for a compromise between speed and accuracy, and limited to modeling just 2 defects. As well, using a Bayesian approach, so introduced a prior distribution on the cost to avoid sort of these non-physical predictions where the rate was coming out 0 for some early pathway in the corrosion pathway. We know that it's not going to stop halfway corroded if left to deteriorate. So we introduced a prior distribution in order to overcome some of the data issues. Multi-phase optimization process was used, so we generate 100 solutions and pick the best 3 as our starting points, run them through a gradient descent optimizer, and then check for convergence. Most of the time they did converge, some of the time they didn't. So we rerun the optimizer from sort of weighted average point, and 9 times out of 10 that was the best solution if they didn't converge. Use an observation-based validation approach to verify this method. So I should say 1/3 of the data was reserved for validation. And for each of the results of the testing set, we ran the model and compared the true and the predicted condition states at the end of the interval, and found that for most asset groups, around 90%, 85 to 90% of the predictions fell within 1 standard deviation. So putting this into the forward model, you can deteriorate defects, you initialize defects in a particular condition state, run the model thousands of times, and then take an average, and then that will give you an indication of what you expect, how you expect those defects to grow. You can aggregate that up to the element level through the inspection, through the reporting module in the PetroNet, and that can give you this minor element condition. Sort of stepwise behavior is due to the inspections revealing the condition, and this is all under like the do-nothing strategy, the deterioration model alone. But really, the utility comes from when you aggregate up to the bridge levels. So there's a small portfolio of 4 bridges. There's no limit on the number of bridges put in other than the computation time. And this shows how we expect the bridges to deteriorate over the next 40 years, or 40 years from the end of the data set. And also show like useful information like the percentage of principal load-bearing elements are going to be in poor condition. They're going to start, with non in poor condition, and then by 2059, we're going to have around 20% of load-bearing elements on Bridge 5 are going to be in a poor condition. The use in this is showing that at some point in the bridge's future, we're going to need to do an intervention. We're going to perform some maintenance work, because obviously, as the bridge experience, as the number of bridge elements in poor condition grows, the risk of failure increases. Again, you can do this at portfolio level. So that's the 4 bridges that we just shown. This is the average condition over all those bridges. And again, we can see that there's an increasing risk to bridge health over the next 40 years without intervention. But this really fits into the wider life cycle model. So that's an ongoing part of work is introducing the intervention modules. So what I'm doing is currently I'm interviewing some people from network rail renewals teams in the regions and finding out how they operate, how they decide which bridge to intervene on. And that's going to get brought into this life cycle model. So I can use this Petri net to model the full life cycle of a bridge, going through the process of deterioration, inspection, intervention, decisions, and application. And then this can be used to recalibrate the deterioration rate. So one of the problems is that filtering process where we have instances of improvement removed. We know that not all interventions, not all maintenance work necessarily results in an improvement. So it's quite a sort of a naive approach, and we know that there's some artifacts of intervention still being left in the deterioration record, which is leading us to under-predict deterioration. So then once we have this intervention model, we can look at how much intervention is taking place that don't necessarily improve the condition, and we can use that to filter out those instances. And then once it's all put together, we can then use it for a full life cycle model, scenario testing different intervention regimes to support network rail in their reporting responsibilities. Thank you.
Thank you. Is there any questions?
On your slide with the predictions, you had kind of jumps.
Yeah.
Can you explain these jumps?
Yeah.
From there, they would go suddenly steep up.
That's due to the inspection regime. So this is revealed condition. So what we've done is kind of assumed that condition stays flat in between inspections. It's obviously not true, but this is just about what we know. So so that's an inspection revealing condition. And because the distribution of inspections is quite sharp, so you have like these quite narrow sort of times when an inspection can occur.
You made the assumption that only the worst 2 defects are going to be taken forward into the model. Is there any case in which you might have, say, multiple mild defects that in combination are quite nasty that you would miss by just looking at the 2 words?
Yeah, I suppose it would, but because of the way that the data works is so sometimes multiple defects are actually recorded in the same inspection because of the way that network will record their defects. So some of that will be captured in those, which is kind of already dealt with by the fact that we've already issued those worst 2 defects kind of include those cases. But that is something that we do miss, and I think I have been looking at ways to allow there to be more defects, but I think the computation times was a real barrier. So I'm just trying to find like a medium between accuracy and just actually being able to compute it. Yeah.
You touched on this a little bit, but did you find any limitations in the data that you provided that didn't make it work? And also, did you include any maintenance interventions that were done as well as the inspection reports?
No, so the data had been filtered for when we have made, so when there's network rails maintenance records are a little bit sparse on bridges. So where there is like known interventions that have occurred, we did remove them from the data set. But the data limitations, I think for inspections, it's quite good. They've got quite a rigorous inspection policy. Most bridges from 2000 to 2019 have at least 2 inspections, which means all of their elements have at least 1 exam pair. But the data sparsity kind of comes from the intervention regime, which is something that I have to deal with now. But yeah, I've removed where we have known an intervention. We've also removed that to leave as much as we can deterioration alone in the data set when we calibrate it.
Any further questions?
Thank you.
Thank you. And our final presentation of the conference is from Mohammed Shafee from the University of Huddersfield on full track experiment to develop remote void detection methodology. I think it should be up there. Okay, just click on that.
Yep. Okay. Everyone, being the last presenter is a bit challenging, but I hope I could grab your attention. My PhD project is about condition monitoring of SNCs, and is sponsored by the Network Ray. But for today's presentation, I'm giving you our results about the full-size track experiments that was a part of Into Track 3 project, and it feeds to my research and it helps my research path. So for today's presentation, I think this is the previous slides I gave to Jacob.
Did you?
Yeah, I gave an updated one.
I don't know where it went. I'm sorry.
Yeah.
Do you know where you put it?
Jacob said that I've updated the last one.
This one.
No, that's
I don't know where he's put it. I'm sorry.
okay, that's fine. I got this one.
Did I not download them? That one. Right. Which one? Mohammed?
Yes.
Yeah.
YouTube.
Yeah. Must have just missed it.
Sorry about that.
That's fine. So I'll go through an introduction of our problem and a methodology of my research, and then go through the laboratory tests that we've done, the results of the parametric studies from the validated FE model that we have, and then the conclusion of future steps. So what's the problem about the SNC is that based on the Network Ray report, they had more than 200 faults in the crossing panels. That these faults happened in 3 years, and it caused lots of costs for the maintenance and also for the delay penalties. That's a very big amount of money that they are paying for that. So the main roots of these problems comes from different parameters that cause the poor crossing performance, including the design, the material failure, support condition, and poor data management. That my research focus on the finding a condition monitoring model that would give us a good insight about what's the current condition what was the past historical condition of the crossing panel, what's the current condition, and what would be the future condition of the crossing panel. So the aim of my project is developing a condition monitoring model for the SNCs, and with the key objectives of gathering data from all different possible source of data that's coming from track measurements, track mounted sensors, or any laboratory tests and physics model, analyzing the data and finding any correlation about the defect manifestation to these data sources, and also trying to find a robust algorithm that could be able and help us to finding the defects that happening in the switches and crossings. So my research methodology, as I said, we are trying to gather data from different sources. First of all, it's from the laboratory test and the physics model, the validated physics model. Also comes from field measurement, for example, the NMT data, the measurement train that's running through the network in the UK, that could give us the track geometry and acceleration and any track embedded sensors. For example, the CONAC system that you may be aware of it, that they are applying and using in the UK and around the world as well. So this data goes to the bank of our data. We are trying to analyze the data, finding any correlation about the specific defects that we are focusing on it, and then feeding these data and trying to train our supervised machine learning model that would help us to apply the model to the field measurement and identify the defects that we will have in the crossing and switches and crossings. So for today's presentation, I'm focusing on the laboratory test and the physics model that we use for the parametric analysis. The key objective of doing this laboratory test at the UKRRIN, at the University of Huddersfield, is to finding and detecting the track properties and void detection by looking at the track responses and the body acceleration in different scenarios and conditions, including different preloads, and also simulating defects underneath the sleepers or the presence of the voids. Here, for the void, I mean the hanging sleepers, the sleepers that they don't have sufficient supports or lack of supports. So this is the raw data that we did a hammer test by hitting different positions on top of the rail, sleeper, and also the axle buckle acceleration, and gathering data from different points, including the rail acceleration, sleeper acceleration, and axle buckle acceleration. The accelerant response of the track, I mean the rail and the sleepers, shows that the rail and the sleepers are vibrating together up to 81 Hertz, and from the 81 Hertz to 230 Hertz, because the first and second mode of the sleepers falls within this range. The sleeper movement is higher than the rail, but in higher frequencies, more than 230 Hertz, the dominant vibrating component is rail. And this is in unloaded and no void condition. So later, for the loaded condition that we applied bogey on top of the track and applying preload of 150 kilonewton, you can see that the track, I mean the track and bogey, rail, sleeper, and axle box acceleration are vibrating together up to 63 Hertz. And from 63 to 167 Hertz, the rail and sleepers is still vibrating together, but the same scenario will happen for higher frequencies. So to understand how the track responds in presence of the void, if we don't have any bogey on top of the track and we hit the rail, the track, you can see that the solid black and red line shows the presence of the void, response of the track in presence of the void, and you can see that the big changes happening at lower frequencies, less than 30 Hertz. So compared to the non-void condition that you cannot see any vibration dominant at the lower frequencies, when we have a voided sleepers, you can see very big changes at lower frequencies. And in the higher frequencies, the rail and sleeper are behaving like non-void condition. So just lower frequencies will be affected. And when we putting the body and applying preload on top of track, you can see that these changes will happen around 95 hertz with a range of 50 to 140 hertz. And this range would give us a good insight that we'll have if we will have void underneath the sleepers. At higher frequencies, the sleeper and body are vibrating like the non-void condition, but the rail is the dominant vibrating components. So these are all about doing tests in the controlled laboratory, how we can extend this knowledge to the field measurement. So here is that the FE model and any physics model could help us to find out how we can extend this knowledge to the field measurement. So we use FE model and use all the properties that we use in the laboratory and modifying the sleeper sections and the whirl ray. And by putting the real parameter values that comes from the instrument test and also from the optimization process that we've done, because we consider different independent and dependent parameters. And then I've done a parametric studies to find out how these parameters will affect the track responses. So in the next slide, you can see that this is the animation. So in this animation, you can see that by changing the sleeper support stiffness, how the track response will change. And it shows that if it works, you can see that by changing the sleeper support stiffness, the track response is affected just at lower frequencies, less than 100 hertz.
Right. Does that work? I'm sorry.
I didn't want to use this one.
We can do it this one. Does it play here? It's not playing.
Cannot play media. I don't know why.
Cannot play media. I'm sorry.
It's fine. So the animation shows that by changing that parameter, just the track responses, the rail response, will change in this range of frequencies. And for the next one, for the rail pad stiffness, when we change the rail pad stiffness, just at higher frequencies, bigger than 100 hertz, the track response will change. So how these kind of parametric studies will help us for further steps is that we change the track parameters and we will find out which range of frequencies will change. So for the next step in our training our AI tools, we say that if we find any changes in track responses in any specific range of frequencies, it could lead us back to say, okay, that track parameters has some problems. So this kind of study will help us for further steps of our research to developing our defect detection algorithm. So for the conclusion, we gained some insights about how putting and different preloads will change the track responses and how the presence of the void in loaded and unloaded condition will change the dominant frequency range of the track response. And on the other side, by doing the sensitivity analysis, we will find out each track parameters will affect which range of frequencies. And then it would help us to identify track defects and refer it back to that track parameters. So for further steps, we are going to studying the moving load on top of the voided sleepers, simulating a void and studying the void propagation, and correlating this effect, how it manifests itself to different source of data, to the axle box acceleration, for example, to track geometry data, and also any track-mounted sensors, and then quantifying these effects and giving them some values using different methods, for example, the RMS, and that could lead us to identifying the effects, developing our algorithms that could help us to identify the effects. Thank you for everyone who helped me in this journey, and thank you so much.
Thank you. I know it's really tough to go last.
No, it's fine.
Very good. Do we have any questions in?
Yeah, I have one. So when you look through your data, it looked like you used voiding parameters between sort of 1 and 4 mil or 1 as a minimum. Is there a reason you picked those? Because kind of 4 mil is quite a low tolerance to maintain. So I'm kind of trying to tempt that fitness in the frame. The reality is less than that can be quite difficult.
Yes, the main reason that we made this one is to find out how increasing the preload will put down the track down and close some gaps in the adjacent sleepers. Right. That's the reason. In the non-preload condition, all of them are hanging and it's no difference. But in the loaded condition, it causes that we could close some of them, and just the main one, it is still hanging. And in higher preloads, for example, 450 kN, all of them are closed, and the track responses were same to the non-loaded, loaded but non-void condition.
Oh, so effectively,
yeah,
you found the limit of how much load you need to take that. And
yeah, exactly.
I think kind of, I guess the question about why you think the bigger void from
it doesn't matter being more than 4 meters because it depends on how much preload you want to apply to that one. So
right.
For our cases that we wanted to apply 150 per kilonewton, that makes 2 adjacent sleepers closed and keeping the central sleepers open, hanging. That was fine. Yeah.
Any further questions in the room? I have one if there's no one else. If you could go back to slide 11, please. So, you say there's at high frequencies the track response remains largely unaffected by the presence of voids. Yeah. There is quite a large difference between the dotted black and the solid black there. Could you explain that spike?
Yeah, just in this case, the black solid line is a rain response, okay, and the red one is a sleeper response.
Not this, the dotted.
The dotted one is a non-void condition.
Yeah.
And the solid one is a voided condition.
But you say it's largely unaffected by the presence of voids. So why is there such a big?
It's mostly just at this 250 hertz. The ray had a bigger response, but mostly the sleeper and the ray.
No, I see. It's mostly similar, but
similar.
That large difference there. That
for the ray, just we have just one peak.
Mm-hmm.
That we couldn't say that this one peak could affected just by the rain. Maybe other parameters is affected there. Because I compared with the other data that we gathered. But generally speaking, if we want using some kind of indexing parameters, for example, RMS values for a range of 30 hertz, we could get better understanding and finding some methods to say, okay, we have voided.
Mm-hmm.
We can just focus on the lower frequencies because higher frequencies is affected by lots of other parameters that the boogie and tracks and anything that comes from in that range of frequencies. So if you are just focusing on developing some tools for detecting the void, the best frequency range would be lower frequencies.
Okay.
Yeah.
All right. Okay. Thank you. Any further questions or comments? Thank you very much. So that's all of the presentations, but I would ask you not to rush off anywhere. We do have another poster session, and this is your last chance to vote for best oral presentation and best poster presentation, so please vote. There should be some teas and coffees next door as well, and at 4:30 we have the presentation of the awards and some closing remarks. So yeah, thank you very much, and go get some tea and coffee and vote, please.
I think voting closes in about 3 minutes, so be quick.
Sorry, just before we move, so I don't know if you just said a quick break till about 4:30. There's plenty of coffee and biscuits, etc. next door. And then at 4:30, Roger is going to close the conference for me, and we'll also announce the winners of the presentation. So don't leave. There's money on the line. And also 50 quid.